Hi. Welcome, everyone. It's great to see you here on the second day. I'm excited to kick off today with an update on MLflow, the open source machine learning lifecycle framework that we launched less than a year ago at Spark Summit as well. So first of all, why have a machine learning lifecycle framework? What's sort of the problem? So the problem is that machine learning development is very complex, and I think anyone who's tried, to build a production application with machine learning can tell you a lot about that. It's a lot more complicated than just a traditional software application. So I want to explain some of the challenges and then explain how a framework like MLflow helps, and then of course give you an update on the things that have been happening in the project. So to understand why machine learning development is complex, let's look at a typical machine learning life cycle. And you can see, machine learning applications have to have this kind of continuous loop where you take in data, you prepare the data, you do model training, and then you do deployment. And once the application is deployed, if it's doing something important, you probably want to monitor it, and you always want to collect new data and update your model based on what's happening in the world. So, machine learning applications have to learn from data, so you need to continuously feed them with, recent, high-quality, relevant data. So that's one of the challenges, is just keeping this cycle going. Second challenge is that each of these steps involves many different software systems and libraries. So for example, your raw data can come from a variety of storage systems, and you really want to combine all the data available to get a really good model. You can't just do one. Your data preparation and training can use hundreds of open source libraries and algorithms, and again, you're always experimenting in machine learning, trying to find the best model and the best pipeline to get the best thing. You can't just say, okay, we'll only use one thing here. And likewise in deployment, once you build a model, you may want to deploy it to a web server, you may want to deploy it to mobile phones, you may want to use it in batch jobs or compare it with previous models, and you need to support all these modes. To make things even more complicated, some of these steps have tuning parameters. So not only do you have to keep track of which algorithms you're using, you also have to keep track of these many parameters that affect performance, and you have to get them right to get the right result. And then there's also the challenge of passing your models between these steps. As you build a model using lots of data sources, lots of data prep functions and so on, how do you get it to work again the same way later when you have to rebuild it? Or how do you deploy it and make sure it's actually performing the same computation once deployed? And then finally, a couple other challenges are just monitoring and governance. So how do you make sure this whole thing keeps working? How do you make sure that it's sort of compliant, or you understand what's going in, and you can fix it if it's not using the right data or doing something wrong. So it's a pretty complicated process, and organizations often have to go through all these steps and come up with a solution separately for each ML application that they build. So really makes it difficult to build these applications. So what are people doing about this problem? Well, one trend that's really started in the past few years is companies building custom machine learning platforms. So some of the best known ones are the internal platforms at large tech companies, such as Facebook FB Learner, Uber Michelangelo, Google TFX. But every company we talk with is actually thinking about this problem and is designing some kind of platform to help with at least some stages of the machine learning lifecycle. So these platforms are very powerful. What they do is they standardize the data preparation, training, and deployment cycle. So as long as you work with the APIs inside these platforms, you get an application or a pipeline that can easily be deployed and monitored and updated. And so they're being used for hundreds of machine learning products at these companies and others, and they really accelerate development and production use. So a really good idea to design an ML platform. But there are also some challenges with the way people are doing these things now. So the first challenge is that each platform is often limited to a few algorithms or frameworks. So whatever the platform developers are able to support and want to put in. And this goes against what I showed earlier, which is in machine learning, you always want to be able to experiment with the latest and best algorithms and frameworks. You don't want to block on, a team because they don't have the bandwidth to support, the latest deep learning framework or whatever. So it creates this kind of tension. And then the second issue is that each platform is very customized and tied to each company's infrastructure, so there's no sharing of common work across them. So about a year ago, we looked at this space, and we thought this is a good idea, but how can we make it better? And we asked, can we provide similar benefits to these platforms, but in an open manner? And that's why we started MLflow, which is basically the first open source end-to-end machine learning platform. So the thing that's different between MLflow and a lot of these existing ones is it's really designed to be able to integrate with whatever machine learning library, programming language, deployment tools or internal process you already have. So it's what we call this open interface design philosophy. All the interfaces are things like REST APIs or command line interfaces or files that are super easy to add around existing code. The project is built out of components where you can easily, swap things in and out, or just use some of the components, and even use it even if you have, some existing pipeline that works well. So the first version of MLflow had 3 components: experiment tracking, projects for packaging reproducible runs, and models, which is a way to package and ship models around. And this is what we started with, but we're also expanding the project to include other things. So when we started this last year, we launched it in June as an alpha release. We really didn't know what the reaction would be to this. Is an open source ML platform a good idea? Is the way we set it up with these components and these interfaces, a good way to do that? And will people actually use it, or will it sort of get in their way or anything like that? So we weren't sure what would happen. And we've been super excited to see the growth of the community since then. So since then, it's 10 months after now, we already have 80 contributors to the open source project. And just for comparison, our team working on this at Databricks is about 8 engineers. So lots of people from outside, and we see hundreds of companies using this and actually achieving really good results with it. So I'll talk more about the community later, but we've been really excited with the growth and with the contributions that have made the project grow. So to give a little bit more background on MLflow, before I'll do that, I'll just quickly show you a few of the components. You'll see them in more detail later anyway. So I'll start with the tracking component just to show kind of the philosophy of the project. So one of the first problems we saw everyone was having is keeping track of experiments and eventually being able to reproduce them later. A lot of things affect the quality of a machine learning model. It's the code you use, of course, to build it, but also the data that goes in, various tuning parameters, and so on. And people had all kinds of manual processes or found it difficult to keep track of these. So what we built is we built this very simple API you can call in your existing code to report metrics and parameters or like objects that you've built up. And then the MLflow tracking API also automatically collects information about your environment, like for example the Git revision of the code that you're in, so you can see the exact same code later. And you can use this API anywhere you are code, whether it's notebooks, local applications on your laptop, something on a server, whatever it is. It's just a REST API that you call from your code, and then this collects the information in a central tracking server, and you get a user interface, an API, to share and compare these results across teams. So what can you do with this UI? So in the UI, you can see all your past runs. You can click on a run and see the parameters and things it's produced. You can produce, complex things like images and files. You can actually take notes about the run later. So if you want to remember additional stuff, you can just add it in there and share it with your team. And you can sort and compare these things in various ways. And we've seen people use this in a lot of different manners. So for example, some people use it for training. They establish sort of a leaderboard and they try different models, or even people in the team compete on, on specific models. Some people use it for production monitoring. You've got something that's being updated every night and you want to quickly compare the metrics and the artifacts produced. So a very simple concept is you've got this agnostic way to log stuff, but there are many ways to use it to help make machine learning development more reliable. The other two components are also pretty simple. So first one, MLflow projects, is just a way to specify, in your code what dependencies it needs in order to run. And basically, you add this file to your repo that explains what it needs, and then other people can run it either locally or they can submit it, to a cluster. And you don't have to spend, 2 days emailing back and forth with someone to figure out the environment needed to run their project. You can just run a command and get the exact same environment. So really good for sharing code. And then the last one, MLflow models, is a similar packaging system, but for packaging models. And in our case, the models can contain, arbitrary code, whatever you want to put in there. So the idea is you can use many common libraries to set up a model, or you can even just write your own code in there, and you get this little package, which is just, a folder of files. And then there are built-in tools that can take the same model and deploy it either to REST serving or batch and stream processing or to debugging tools down the line. And all those things can be agnostic to like what library was used to build the model. So this is really great for handing off the model between users, between teams with different expertise, getting the same result. So that's a quick tour of the project. Just to go back to the community, so as I said, the community's already grown quite a bit. We like to track how many people actually send patches. So we've got 86 contributors already from more than 40 companies. And then the other exciting thing is, what kind of patches are people sending? So we've gotten a huge number of large external contributions from companies outside Databricks. So these include, the database storage backend, integrations with lots of libraries, Docker packaging for projects. This was actually contributed by a company in Brazil, like an energy company. Plugin system, the R API, which was contributed by our studio. Lots of new visualizations. These were contributed by a financial company in New York. So many interesting sort of features, a lot of things we hadn't thought of, but that make the project better, and coming from around the world as people are using this. To put this in context, I was also involved early on in Apache Spark and working with early users and trying to build a community around it. And for Apache Spark, even though there were people using it early on, it took about 3 years since launch to get to 80 contributors. And for MLflow, we got there in about 9 months. So we're really excited with about the interest in it, and we want to keep growing this project and fostering a really great community for everyone involved. Okay, so that's that. Another way to kind of showcase the growth of the project is some of the integrations that are built into it. So when we launched this last year, MLflow only supported Python, and it had 3 libraries that it could automatically capture models from. It had a couple of storage backends and a few deployment systems it could deploy to. And now all these things have grown. So now we also support Java and R. Lots more libraries are kind of built into it, so you can easily capture models. Many more storage backends, a lot of deployment systems. Actually, the Onyx one is one that I'm really excited about that's currently in development in a pull request. So that's also exciting to see, and I think a year from now we'll see even more logos on this slide. And a little bit about some contributors. So these are all, the ones at the top are ones who've given public talks about it. So Edmund and Brandless are 2 Databricks customers who spoke at the MLflow meetup here in February. And Comcast, Showtime, and Gojek are all talking at this summit. Comcast is actually talking right after me, so I won't steal their thunder, but they're doing really cool things with it. Gojek is also a very cool company. It's a huge, ride-hailing and everything else app in Southeast Asia, and they've been using MLflow as well. And of course, we have other tech platform companies using it. We heard from Microsoft yesterday. Our studios contributed a lot, and Splice Machine and Faculty are 2 other companies that are building products based on it and contributing back. So the one sort of major announcement on this front at this summit is Microsoft joining the MLflow community functionality and actually adding the MLflow tracking API in Azure machine learning as a way that they can capture results. And so we're really excited to see that. And to talk more about that, I'd like to call up Greg Buehrer, who's the chief architect of Azure machine learning, to give you a quick demo of MLflow over there.
Thanks. Hi, I'm Greg Buehrer, Chief Architect of Azure Machine Learning. I'm very much on the dev side of things, so talking in front of 45 billion people with brand new software and doing a live demo, this should be pretty interesting. So what is Azure Machine Learning? Essentially, it's a set of managed services that handle this machine learning lifecycle that you saw and heard Matej talk about a little bit ago. There are a lot of complicated steps, as he talked about. We have a lot of sort of custom things in Microsoft that try to make that easier for you, including FPGAs, custom hardware, special featureizers, AutoML, hyperparameter tuning with hyperdrive, a lot of services like that. One of the really important services, as Matej was pointing out, is experiment tracking. When we started our experiment tracking service 2 years ago, there really wasn't an open source standard. But in working with Matej and Andy and the team over the last, say, year, mostly on deployment on Azure for ML models in MLflow, we realized our philosophy around experimentation was really quite similar. And then in looking at that, we said, hey, how can we snap to this open source standard? It has a ton of energy. It really fits what we're looking for. And so that's, over the last couple months, that's what we've done. And what I want to demo to you today is native support for MLflow in Azure Machine Learning for your experiment tracking. OK, so the way I'm going to do that is I have this notebook. It's a Databricks notebook. It's running on a Databricks cluster. And I'm going to launch 2 training jobs. One experiment training job is going to be native in the cluster. One experiment job is going to be running on a remote MPI cluster. And what I want to show is it sort of doesn't matter where you train these things. You can move all these things to a common experiment tracking platform in Azure and then leverage the power of Azure across all your products. So the first thing you need to do is you need to set the URI of your tracking server. This is, if you've used MLflow before, you know this is the first step. I've linked my workspace in Azure ML to my workspace in Databricks, so all I have to do is make this one function call, and now I'm set to track to Azure. The next thing I do is I set an experiment name. This is really just a string that allows you to group runs, so they're easy to compare against each other. If you've used MLflow, you're very familiar with this. And you can see I'm just using the standard MLflow client that you can get in the open source community. OK, the actual experiment I'm going to run, it's basically, it's MNIST. So what it does is it looks at handwritten digits, and it tries to detect what the digit is. It's not super important for the demo, but I just thought you should know. I'm going to use PyTorch. The important things to look at here are that I'm logging my metrics with MLflow here. I'm logging more metrics with MLflow here. And when I run, I use MLflow start run, which is standard MLflow procedure. And when I'm done, I'm going to log my model, my PyTorch model, using MLflow. So let's get that kicked off. Appears to be running. OK, so it's off and running. The next thing I want to show is I'm going to launch a remote job. It's essentially the same job. It's using the same MLflow APIs, but it's on this remote cluster. So I have to do a little gobbledygook here to set up the environment. I've actually already provisioned the cluster. So if you look at this, these 3 green lines, you'll see that the cluster's been set up already. I'm not going to run them again. But the cluster's name is CPU cluster. And then all I have to do is say experiment equals new experiment, experiment submit. And now I have a job running off in this remote cluster. So the purpose of this fairly busy slide is to tell you that you can use MLflow. You can train anywhere. You can train in Databricks. You can train with any framework. We'll then package that up in a Docker container, and you can host that Docker container anywhere. You can host it inside Azure's cloud. You can host it on the edge. You can host it in heavy edge, or you can host it locally. You can pretty much put it anywhere, and then you can still use a common framework to collect your telemetry. So let's jump over to our experiment tracking service API. Let's try to refresh that guy. I've run this job a lot of times, so you'll see there's a lot of experiments in here. We've run it 67 times. This is the amount of time each one took, and the average loss, it's automatically tracked this. You can see here the 2 jobs I just launched. One of them finished the local run. The remote run is still running. Let's see if we can get a look at that. So you see here it's go ahead and it's logging in real time, which is pretty cool. I can come up here and look at what my different compute targets are. So we mentioned we have these compute targets. We track these compute targets. We know when you train that job, what compute target did you train it on. If you generated a model, you can register that model. Here I have 3 models registered. You increment your version so you know exactly what model was trained with what data. And then you can take that model and you can deploy it. As I showed you before, it's really easy to deploy. So I deployed one earlier today. I don't want to take up too much time now doing that. But here's the deployment. And you click on that deployment, and it'll tell you, hey, what models were in that deployment? What version of that model was in the deployment? So all this is tracked for you. So now, if we go back to our demo here, basically this is, when I did build this scoring container, I just used the standard MLflow scoring container API from MLflow, and then I just deployed it on Azure using Azure ML. Now, I need to get a handle to that because it's actually a real live URL. So I've got the URL, and now I've sort of made this, these helper functions, but I'm going to try to see if it actually works. So I have 1,000 random images of digits. I'm just going to pick one. It's a 7, I guess. See if we score it right. And we scored it a 7. So yay, it worked. So just to summarize, we have all these services in Azure ML that are really powerful. We feel they really help customers. And now we have an open source API to use MLflow, which we're really excited to be contributors for. If you have any questions, just ping me. If you want to try it out, just ping me. And thanks for your time.
Cool. Thanks a lot, Greg. Yeah, that's super exciting to see. And the Azure team has been contributing a lot to the things that are going, into the next version of MLflow. So the other thing I want to talk about in my presentation is kind of what's next for the project. And I want to mention a few different things. So first of all, the next release coming out is MLflow 1.0. This is already in active development, and it's going to be finalized this May. And it basically stabilizes the API in MLflow for long-term use. It fixes a few small things that we discovered as it was being developed. And it also adds many frequently requested features. So for example, better search UI, Hadoop file system storage has been merged in, X coordinates on metrics, simpler commands to use it, pagination, Windows support, various things that people have been asking for. So this is in active development. We're excited to see it coming soon. And then the other thing that we want to do, as people begin to use the project is a new component. So we've been trying to get a lot of feedback from the community. For example, we ran this survey at the start of the year on our website, got a lot of responses on that, and of course we talked to a lot of active users as well. And when we started the project, we always kind of designed it to have these modular components so that we can add new ones in the future. And today I'm excited to announce 2 components that we've been prototyping and developing at Databricks that we plan to roll out later this year. So the first component is MLflow workflows, which is a way to easily share and edit multi-step pipelines. So with MLflow workflows, you can define a multi-step pipeline in code by calling a few different projects, but then you can also see it in the UI and actually edit it and resubmit it with new parameters. So we found people often want to just quickly change a few parameters or change which step they're using without going back to the code and figure out how to build everything from scratch. And we might want to make that easy. This workflow system can also automatically reuse results. If you ran a step before with the same parameters, we can reuse it. And also, when building this, like the rest of MLflow, we wanted it to be easy to integrate with existing infrastructure. So we didn't want to create, yet another new workflow system. So instead, we designed it so it can run on existing job schedulers like Apache Airflow, various other schedulers as well. So you can just plug it in and run these workflows on your platform of choice. So we think this will help a lot with sharing and editing complex pipelines. And then the second component is actually the most demanded component in our survey is the MLflow model registry. So this is special sort of new features in the tracking server that let you manage, tag, and version models in the server, and then also keep track of where they're deployed, which version is deployed, and so on. So you can take anything that you packaged in the MLflow model format and register it as a registered model. You can have different versions of one. You can deploy these things to various inference systems. You can also see who's using the model and add metadata about it, like notes. And this is also something that we want to to plug into existing registry systems people have. So it's not a new thing you have to manage if you already have a way of of managing models. So these are two things that we're building. And to show you some prototypes of these and a demo, I'm excited to introduce Aaron Davidson, who's a staff engineer at Databricks, and who will give you a demo of these new components.
Hi. Hello, everyone. Excited to be here. I'd love to stop and chat, but we have a lot of material to work through, so let's get started. Today, we'll be working on a relatively simple recommendation use case. But we'll see how even in this simple use case, we'll run into some pretty complex problems when we try to build a production-ready, end-to-end machine learning system. So we'll be recommending tweets to users. I already have an endpoint deployed, but right now it actually ignores the username and just returns popular tweets. So for example, we see a haiku, we see a tweet about Beyonce's Google Calendar, and we see a tweet about, it's a motivational quote. So these are all perfectly good tweets, but they don't really speak to me. I'm a very simple person. I like two things: companies going IPO and cats. This is neither of those. So how can we make a model that speaks to me? We might train a model like this. We might take tweets and produce tweet embeddings, where we map tweets to a vector space such that semantically similar tweets are close to each other. We might then take those tweet embeddings and produce user embeddings so that users with similar preferences are also close to each other in that same vector space. We might then create a training data set based on how users have interacted with tweets in the past. With all three of these inputs, we can produce a ranking model where we recommend specific tweets to specific users. Even in this simple workflow, though, some problems arise. For example, what if different teams own different steps? What if different parts of the pipeline are written in different languages, like Python versus Scala, or different frameworks, like TensorFlow versus Spark ML? What if some parts of this code are in GitHub, other parts are in a local IDE, and another one is in Jupyter? How do we string together all these different steps to make a reproducible pipeline for the best results? And once we have good results, how do we actually take those results and deploy them to production? How do we do that deployment? Once we deploy it, how do we update it? And how do we track what's going on where? So let's start with the multi-step workflows. So this is the new component coming in MLflow. And we can see it's a very simple definition language for defining tags. So in this case, we have a step called tweet embedding. This is pointing to a Git URI. At that URI is an MLflow project, which Mate talked about. This project contains the code for this step, as well as any dependencies, such as a conda YAML or Docker file. We can also pass in parameters. In this case, we pass in today's date. So we want the most recent tweets. We have another step for creating a training data set, and another step for user embedding. This one's interesting because it depends on the tweet embedding step. So here, this syntax says that the tweet embedding step will output its artifacts to a cloud storage location, like S3 or Azure Blob Storage, maybe HDFS, and the user embedding step will pull that in to run. Finally, we have our training step, which also is like GitHub, takes all the other inputs as parameters, and then has its own regularization parameter as well. To give you an example of one of these steps, let me dive into the training step. So this is the GitHub code that underlies the training pipeline. And what we can see is, we take the user and tweet and scoring information and produce a combined embedding. We take this combined embedding and score and train a simple linear regression model on it, where we're going to learn the weights of each of the features of the embedding. Given this linear regression, we log the F1 score using MLflow. The F1 score is just a combined precision recall metric. And then we log the actual model as an artifact, which we'll use to do the actual serving at the end. So that was the example of a single step. Now let's run the entire pipeline. We'll open here now the MLflow UI, and we can see this new visualization, which shows how the DAG is executing. So in this case, the tweet embedding and training dataset steps are executing in parallel because they don't have any dependencies between each other. And as they complete, the next steps start running. We can also see this graph in JSON form. This is the same exact information, just as JSON. And we can also see it as an Airflow pipeline if we want to run it in that context. So as these steps complete, we can observe the metrics and parameters that came out. In this case, for example, we see an F1 score of 0.44, which is actually pretty bad. This might be because the regularization is 300, which is an insanely high value. So what I can do now is I can come up here and rerun this pipeline with different parameters. So I can just hit this button, and now I see an editor where I can edit this JSON, and I'll change the regularization from 300 to something more reasonable. I hit OK, and it submits a new run of this pipeline. We can go to that run. As we see here, something interesting to note is that the first 3 steps were all cached. If you recall, they were keyed on today's date. And because we've already run them for today, MLflow has automatically reused those results and just reruns the training step. This allows us to iterate much more quickly on the parts that changed. So we can open the training step, and now we see an F1 score of 0.86, which is good enough to go to production. So I'm going to scroll down here to my artifact. If you recall, we logged that Spark ML artifact, and here it is. I can now register this artifact as a model. I'll create a new model called tweet recommendation, and this will register the first version of it. So now this is the MLflow model registry. It's very simple. But what we can see is that it's pulling from that run. So it has one version of this model based on that run that I created. And I can take this and deploy it. So I can deploy it to my favorite cloud service, like Azure ML or SageMaker, or just do a Kubernetes. In this case, I'll pick Azure ML. And I'll hit deploy. And this will actually spin up a container in Azure ML. It'll create an endpoint, which I can then ask questions like, give me recommendations for this user. As this is happening, though, I remember something my good friend Brooke told me. She said that neural nets are way cooler than linear regression. I also happen to know that she wrote a MLflow project that takes tweet embeddings and user embeddings and produces recommendations. So although I now have my endpoint, let me actually go back and train another model and see if it does better. So here's my workflow. I'm going to change the name of the step. I'm going to change the code from pointing at the linear regression to pointing at Brooke's code. And instead of regularization, I'll have a hidden units parameter. I'll set it to 5. OK, so this runs a new version of this workflow. I come back to the MLflow UI. Again, I see that the first 3 steps are cached, and we're only running the train neural net step. One cool thing to note here is that Brooke wrote her code in TensorFlow. If you recall, my code was Spark ML. As long as it takes the same inputs and both produce an ML model, it all works out. I don't have to understand what the code is actually running. Here we see an F1 score of 0.93, which is even better than my 0.86 from before. So I come down here, I see an ML model. This one is a TensorFlow model, but it has the same input-output schema. And so I'm going to register this to the same model, and this will create the second version of this model. So I can come here, see second version. I'm going to update my endpoint from version 1 to version 2, and this will just take the existing endpoint and upgrade it to this version. I can now copy the endpoint for this new model as this gets deployed, and I'll come over to my inference code and now paste in the new URL. So I have new URL running. Now, if you recall, I only like 2 things, companies going IPO and cats. So let's see how this does. So the first tweet is about Pinterest going IPO, pretty solid. The second tweet is about petting a cat, also solid. The third tweet is about an IPO of a company called Crypto Blockchain Kitty Catnip. That is surprisingly irrelevant. So we've seen how we can use MLflow, especially the new components of the MLflow workflows and MLflow model registry, to create an end-to-end production-ready machine learning system. Thank you.
All right, thanks a lot, Aaron. And just to wrap things up, I have one more quick announcement for you, which is, for users of Databricks, the managed MLflow on Databricks is now generally available on both Azure and Amazon Web Services. And yeah, that's exciting to hear. Yeah. Yep. And if you're not familiar with it, the way that we're integrating MLflow in Databricks is it's the same client library, it's the same code you'd run anywhere, but we've integrated it into the graphical Databricks workspace. So for example, if you are in a Databricks notebook, you're using the MLflow API and creating runs, there's this sidebar where you can immediately see your results, and then you can also click on any past run in the sidebar, and it's actually integrated with notebook version control. So it shows you a snapshot of the notebook as it looked back then when you had that version. So very simple integration. This is the kind of thing we hope to see in other products and IDs as well, to really bring these ML lifecycle processes kind of to the forefront as you're working with with your code. Finally, if you want to get started with MLflow, it's very easy to get started with pip install, and there are a lot of docs and tutorials at mlflow.org, and we'd love to hear what you end up doing with it. Thanks a lot.